everyone to today's event, Firing Up the Quantum Future, presented by SGInnovate and partnered with Center for Quantum Technologies, in conjunction with Deep Tech Summit 2020. I am Ziying from SGInnovate, and if you're new to us, we are a government-owned organization in Singapore with the mission to build deep tech innovations from Singapore for the world. We invest in and help build deep tech startups in the fields of artificial intelligence, medtech, and quantum tech, just to name a few. We work with entrepreneurial scientists and clinicians to help bring their innovative research from lab to market, and we also develop tech talents and engage with a vibrant deep tech ecosystem. As a lead up to our Deep Tech Summit happening tomorrow at Singapore's Week of Innovation and Technology, we are glad to have Professor Michael J Biercuk, CEO and founder of Q-CTRL, here with us to present a keynote on starting up the quantum future. This will be followed by an exciting panel discussion with fellow quantum thought leaders, Dr. Joe Fitzsimons of Horizons Quantum Computing, Dr. Ng Hui Khoon from Center of Quantum Technologies, and Dr. Mattia Fiorentini of Cambridge Quantum Computing. Just some house rules. During the webinar, if you have any questions, please post them in the Q&A box at the bottom of your screen, and do feel free to use the chat box to connect with our wider community. Without further ado, let me hand over the time to Professor Biercuk to start his keynote. Professor, please.
Thank you very much for the introduction. It's great to be here. Let me just bring up my slides. I hope everybody can see those now. It's a real pleasure to get to speak to everybody. My name is Mike Biercuk. I'm a professor of quantum physics and quantum technology at the University of Sydney. I'm also the founder and CEO of Q-CTRL. And Q-CTRL is a company that I started in 2017 that's focused on our expertise in something called quantum control engineering in order to build a new generation of technologies. And that new generation of technologies functions because of quantum physics. And what I want to tell you about today is some background on this field, and then some lessons about deep tech startups, especially in quantum technology, or using quantum technology as an example. Now, we're excited about this particular field because quantum technology promises to be as transformational in the 21st century as harnessing electricity was in the 19th. And I mean this not just because it's the newest and shiniest thing, but because there are deep parallels in the way we learned to first access and then harness a new physical resource in the flow of electricity, and how we're doing the same thing right now when it comes to harnessing quantum physics as a resource for tech. Now, there's a lot of excitement about this field, and we hear about it almost every day in the media. This is a chart that many people on this call will be familiar with. This is called the Gartner Hype Cycle. It lays out emerging technologies and talks about...
Sorry, Professor, we can't see your slides. You
cannot see my slides?
Yep, we are seeing your full screen currently.
Oh, well, that's...
Yep.
So it's the first time I've messed that up in my career.
No worries.
I'm not sure why it's not letting me show my slides. Hang on one second, please. I'll do something a little bit different. I promise everybody we tested this.
Perfect.
Can you see that now? All right, I have to jump back just a little bit. So here we are back at the Gartner Hype Cycle. You didn't miss anything. I just had some words on the previous slide. This is a chart that illustrates the development of emerging technology. And in particular, it shows how we can overhype things. And so we have what they call the innovation trigger, the peak of inflated expectations, the trough of disillusionment, the slope of enlightenment, and then the plateau of productivity. Now, this particular version is from just a couple of years ago. Not much has changed since then. And what you'll see is that on this chart, we have the emergence of one of the first applications of quantum technology. This is one that many will have heard about, called quantum computing. The idea of encoding and processing information using quantum physics as a resource. With this in mind, and all the excitement that's going on in the community, it's useful to ask the question, what is going on? And to understand that, we have to take a step backwards and ask, how does this new quantum technology relate to the technology that we have right now? Well, the start for that is modern information technology, modern IT. And many of you will be familiar with this image. This is a picture of microprocessors. These are the fundamental devices that we use to process information today. They are used in the laptop driving this presentation. They are used in server farms. There are many of them in your car, and there's even some of these in your dishwasher these days. These are devices that fundamentally work because of quantum physics. The fundamental logic units are called transistors and either allow electricity to flow through them, like in a wire, or block the flow of electricity, as in an insulator, depending on the application of another electrical signal. Controlling the flow of electricity with electricity comes to us because of quantum physics. And today we can make really spectacular devices in this way. The most modern devices have well more than 1 billion of these switching elements, these transistors, in a chip roughly the size of your thumbnail. You can build truly magnificent things. But the way we build technology right now is a little bit like this. We start with a large pile of stuff, and then if we learn the right rules, we can shape the stuff, the matter, into a form that is useful for our purposes. In this case, you see a great example of a sand sculpture, where starting with a giant pile of sand, you can shape it to here a magnificent form. This is Freud with a patient on the couch. Now, this is similar, again, to how we can shape these magnificent forms on the surface of a semiconductor with 1 billion transistors in the shape, in the area the size of your thumbnail. But it shouldn't escape your understanding that if instead of looking at the giant pile of stuff, if instead you look more closely, that you would see there's a new level of complexity that emerges. That instead of a homogeneous pile of tan sand, you see that the individual grains of sand are diverse, that some are seashell and some are stone, some are transparent, some opaque, some are dark, some are light. None of this is visible to you when you only look at the giant pile of sand. It only becomes apparent when you look closely enough. And this lesson carries over to the way we build technology. That in what we call the second quantum revolution, we're looking to build a new generation of quantum technologies that harnesses the most fundamental particles of light and matter as our building blocks, as our grains of sand. And we can start here with this cartoon representation of an atom, a building block of matter. And before anybody objects to trying to build technology that starts with individual atoms, individual particles of matter, well, here is a photograph from my academic laboratory of one atom of a species called ytterbium in a special kind of electromagnetic bottle called an ion trap. This is a technology that won the 2012 Nobel Prize from my former supervisor, Dave Wineland at NIST in Boulder, Colorado, and enables us to access for the first time these individual grains of sand, our fundamental building blocks of this new generation of technology. Now, it's a new generation of technology because when we look closely enough at this size scale, new complexity emerges. Instead of having to think about individual atoms like billiard balls that are solid and bounce off of one another or can bounce off the walls of a container, we have to think of them in a different way. We have to think of them more like waves. Waves that can spread out in space like ripples on a pond. Waves that interfere with each other or even with themselves. And on these size scales, nature even seems to have its own form of magic. Through something called quantum entanglement, particles can become linked together such that they really can't be described as individual particles anymore. They can only be described as one composite object. And this is something that Einstein pejoratively called spooky action at a distance. Something that he thought was too strange to be part of quantum tech, to be part of reality. And yet we've discovered that in this particular respect, Einstein was wrong. And that beginning in the 1980s with devices like this is an ion trap, we began isolating the individual atoms, isolating our individual grains of sand, and demonstrating that this picture of nature that's given to us from quantum mechanics is real. It is what describes reality. And since then, in particular since the mid-1990s, we've engaged in a quest targeting how we can access and leverage this physics to do new and useful things. This is the genesis of quantum technology. Here you see an application with an ion trap for quantum computing, that application I showed on the Gartner Hype Cycle. Now, I know many of you will have heard of quantum computing, and I wanted to spend just a moment or two talking about it. Today, quantum computers are largely at research stage. We are building and testing new approaches to encode information using quantum mechanics and process it to gain useful insights. And it's very important that we understand, in addition to that, that quantum computers are not useful for everything. They are potentially useful for certain very hard problems. And I've called out one class here: problems in the simulation of chemistry or of materials, which can be relevant to pharmaceutical industry, to industrial chemistry and the like. These are problems that currently face major computational bottlenecks, where it's very, very hard to perform the computations needed to do, say, drug design, or to design a catalyst for an industrial chemistry problem. When we try to encode that problem, which involves atoms interacting and is governed by the rules of quantum mechanics, we end up with a blurry, pixelated image of our problem. We're taking a quantum problem and we're squeezing it into our laptop or even a supercomputer. And in so doing, we lose fidelity of the representation. So instead, with quantum computing, we're looking not to take that quantum problem and map it onto a classical computer, but rather onto a quantum computer. Now, intuitively, that makes some sense. We're using the same rules of physics. But what's interesting and exciting about this, especially in the near term for enterprise applications, is that we don't need a solution which we can prove analytically with pen and paper is going to give us some exponentially large benefit at some distant time in the future. All we need is a less pixelated image. All we need is a slightly better approximation in order to have economically and industrially relevant benefits. Now, what very clever people in the algorithm space have figured out is that these problems in chemistry and physics and material science actually can be used to represent problems in finance, problems in portfolio optimization, problems in logistics, problems in transport networks. Much like if you're from the economics background, you know that Black-Scholes is using something called the physics of diffusion. This means that totally new problems become accessible with quantum computers. And so there has been the emergence of a sector in heavy industry, in incumbent industries, looking to build quantum computers, and also an emerging space of startups. And this is where I want to spend the last few minutes of this presentation. We think a lot about the tech sector, and we think about the tech sector often when we think about quantum computing because we think about the contributions from, say, Google or Microsoft to this field. But as I mentioned, there are many startups working in this space. And there's an important distinction to make for the investors who are in the audience today, or the young budding entrepreneurs who are interested in getting into the space, a distinction between tech broadly and deep tech. And I think this obviously quite contrived analogy really does in fact capture very well the distinction that in tech, we hear about a small number of consumer-facing products that may have a very big footprint, but there's so much more that fundamentally enables it. And all of that, by this analogy, is deep tech. It's this whole sector of emerging engineering and development that then powers consumer products. And I wanted to differentiate a little bit more for those of you who are interested in getting into this field. If you think about tech on the left here, we're thinking about general businesses that will leverage existing capabilities, that will leverage existing functionality in, say, hardware or in software, where there may be a well-established market where a user wants to scale very rapidly to provide services to a large number of customers. And in the shape of the business, almost everything is about product development and sales. By contrast, deep tech has a very different focus across these three points. The first is that fundamentally, the effort of that company will require new technical research and development. So that means that there is a large capital expenditure that's generally implied and a longer growth period, because the market is not established in simply waiting for a solution to be delivered. In many cases, the market develops alongside the startup itself. And because the technology has to be developed, it takes time for it to come to market. And then from a business perspective, in addition to having to do the research, the funding will often involve contract projects and external R&D funded by, say, public sector industry or public sector organizations. So it's not just take your product and ship it via a standard software as a service model. There's often a lot of different engagement with both public and private sector organizations in order to make these companies work. So I wanted to now share 6 lessons that I've distilled, again, for the budding entrepreneurs, and hopefully of interest to the investors here, about building a deep tech enterprise using Q-CTRL as a model. Q-CTRL is the company that I founded. The first lesson, the first key message, is to find and solve a difficult and impactful problem. In the context of Q-CTRL, we focus on the fact that quantum systems are extremely unstable. I gave you the great story about how exciting quantum technology is, about how impactful quantum computers can be in chemistry and drug discovery. But I didn't tell you why they're still so small today. It's because the hardware is extremely fragile, and over a very short period of time, the hardware breaks. And you can't perform computations with it anymore. For scale, we can compare the performance of quantum computers to conventional machines. And using metrics that are designed to be similar or comparable, we can say that a transistor, the fundamental logic elements, the switching units in conventional computers, can run for about 1 billion years at 1 billion operations per second and never be likely to suffer a hardware fault. That's why computers are so powerful today. But by contrast, in a quantum computer, the community average, if you will, is that the individual quantum carriers of information, called qubits, live for about 1/1000th of a second. This is like 24 to 27 orders of magnitude difference, depending on the details, in how susceptible quantum computers are to error. This is the problem that Q-CTRL attacks in quantum computing. We produce something called quantum firmware, which improves the performance of the underlying quantum hardware, such that our colleagues who build quantum algorithms or software development infrastructure, like Joe's team that you'll hear about in the panel discussion, that these organizations have useful hardware on which to run. And we've shown that these approaches work really well. That applying these protocols on existing cloud infrastructure from, say, IBM or other services, we can get 10 times improvements in performance across a wide variety of metrics that are relevant to how big or how complex an algorithm you can run, and also have huge impacts on the providers themselves in terms of the value that they can extract. Point number 2 is to find points of differentiation. In the context of quantum technology, there are companies that make hardware, people who build quantum computers. There are companies that make software, companies that are writing algorithms to program on quantum computers. Entropica Labs that we saw in the video in the beginning does that kind of work. Q-CTRL is different. Q-CTRL has the capital intensity of a software enterprise, but we are able to deliver value on a different timescale because we are providing infrastructure software, not end user software. So we sit between hardware and software. And as appropriate, we also build prototype hardware, although we don't manufacture as part of our business model. Next, leverage public investment. In Australia, where Q-CTRL is headquartered, we have a large number of players who have for a very, very long time been extremely active in quantum technology. They've been funded by US agencies. They've been funded by Australian Defense, Australian Research Council. They span all the major research universities. They span multiple what are called centers of excellence. And just like Singapore, this has built a community of experts who have something really unique to bring to the table. It was from my academic team and then my colleagues whom I recruited to join Q-CTRL that we drew expertise in order to build something really unique in Q-CTRL. And if you're building any deep tech enterprise, you really do get a running start if you can tap into that community of researchers. Of course, Singapore is extremely well positioned in a similar way with the various universities, NTU, NUS, and the like, A-STAR, all engaged actively in this community. Lesson 4, find a balance between research and business. Q-CTRL now has the world's largest concentration of expert quantum control engineers, 25 people at the PhD level or equivalent who focus on quantum control engineering. But we have a team that's almost as big, focused on product development and business development. That we focus as much on our customers and our users and their experience as we do on building new technical solutions. This is an essential lesson because many deep tech founders will make a mistake, if you will, to replicate themselves, to just hire more people just like them with the same skills and the same background as they build their enterprise. If you're doing deep tech enterprise, you also need people who come from the business community, who come from product engineering, who focus on what the customer really wants and understand how to deliver value to them as much as the core technology that you're developing. Lesson 5, find investors who understand. We're very fortunate to have a collection of tier 1 VCs who've supported us since our inception. These are globally distributed: Australia, US, China, Hong Kong. They span organizations that focus sometimes a lot on consumer products, sometimes a lot on really science-driven exercises like DCVC, but all of them understand that deep tech is a long-term play, that this is not 6 months to a mobile application to sell wine. This is something with a much longer time horizon, which requires a different kind of investment and a different kind of investor patience for delivery of major value, but where the outcomes can be transformational, both economically and societally. And the final message that I'll use to conclude the talk is that in deep tech, the exciting thing for us is to identify and embrace greenfield opportunities. That again, in the context of Q-CTRL, we're using control engineering to improve the performance of quantum hardware, of quantum technology. And we've seen in the history of technology that control engineering has built industries before. You can see this in the Wright brothers, who brought control theoretical concepts to the development of aviation. And the story is the same today in drone technology and walking robots and effectively anything else that you're seeing emerging. Control has always been an enabler, and control has built industries repeatedly through history, and Q-CTRL is looking to do the same. We're excited for the opportunity to build a completely new industry alongside our partners, our customers, and our colleagues around the world. So with that, let me thank you very much for your attention. I'll hand back to the organizers to take us to the next panel. I'm very excited to have a little bit more of a discussion about this field. So thanks so much for your time.
Thanks, Michael. Can I maybe invite all our panelists to turn on the video? Hi, everyone, and nice to see you, Mattia. And welcome to today's session. We currently have about 86 participants in total, and everyone's kind of probably interested to find out, a couple of questions, right? I've seen, I see one question already in the Q&A. So for folks in the audience, if you guys have questions, feel free to type it in the Q&A and upvote the ones that you would like us to ask at the end of this. We only have about 35 minutes for the panel discussion, so I'm going to run through the questions as quickly as I can. So maybe as a start, let's get everyone to do introductions. I'll ask everyone to perhaps share a bit more about the company, what they do, and maybe if you can limit that to about 30 seconds, that'll be perfect. Right. So I'll start with myself. My name is Victor. I'm a director of venture investing here at SGInnovate, and I work on leading all the deals within our organization in across all the deep tech sectors that we cover. Maybe Michael, you want to go next?
Sure. I'm Mike Biercuk. I'm the founder and CEO of Q-CTRL. If you missed the beginning of my presentation, I'm also a professor of quantum physics and quantum technology at the University of Sydney. And I'm happy to talk some more about Q-CTRL in the next few minutes.
Thanks, Mike. And Joe, can I get you to introduce yourself next?
Sure. I'm Joe Fitzsimons. I'm the founder and CEO of Horizon Quantum Computing. We focus on building tools to bridge the gap between classical computing and quantum computing. And in a former life, I was a professor as well.
Thank you, Joe. And Hui Khoon, can I get you to introduce yourself next?
Yeah, hi everyone. I'm Ng Hui Khoon. I'm an associate professor of physics at the Yale US College and also with a joint appointment at the Center for Quantum Technologies in NUS. My group actually works on a little bit more upstream research than many of the people here, but really is largely focusing on controlling noise in quantum computing systems.
Thank you, Hui Khoon. And Mattia, can we get you to introduce yourself next? Oh, sorry, we're not getting your audio. I think you may be muted. Oh, you're not muted. Oh, still no audio. Okay, here we go. Thought I heard something. Maybe while Mattia's getting ready, let me maybe start with a quick question. You know, to kind of like, here we go. Nope, still not getting it. Sorry.
We promise. We did all sorts of testing of this beforehand.
Yes, we did. Okay, well, while Mattia figures that out, maybe I can quickly start with a question. Oh, hang on, let me see. No. Okay. I'll maybe Mattia, you try and figure it out, and then just signal to us when you're ready to try. Just shout, you know, and we'll make sure to stop. So I guess the first question to kind of ask as a follow-on, you know, to Mike's presentation, right, is what is the current state of quantum software and its potential impact, right? And also the follow-up to that is, what do you believe is a realistic timeline for us to expect, you know, the quantum hardware to catch up with the pace of quantum software? Right, so you did mention that the hardware tends to get broken, you know. And we always hear about, you know, hardware being the laggard in this instance, right? So what are your thoughts around that? Anyone, please?
Well, maybe I'll start and
Sure.
then give over to others. I think the first point to make is that software has many faces, right? There are many different kinds of software. The kind of software that Q-CTRL builds is not at all similar to the kinds of software that either you know, Horizon Quantum builds, or the kinds of software that people typically talk about when they say quantum software, right? Mm-hmm. Typically what they mean is software to run programs on future quantum computers, right? And we mean something different. We mean the infrastructure software that makes quantum computers actually function well. And you know, another part of this is that when you're thinking about the applications and the way you build software for quantum computers in this this application or end user focused approach, mm-hmm. we've largely been stuck in doing it with pen and paper, right? Most of the original algorithms were written down in pen and paper. Imagine trying to write Windows with pen and paper, or Microsoft Word with pen and paper. That's the status that we've been stuck in for a long time. Mm-hmm. And it's through, say, the research going on at US, or the tools being built by Horizon Quantum, that frameworks are coming in place to help developers actually start building things that leverage the existing hardware we have. So maybe I'll hand over to others to comment as well.
Sure.
Sure. So if it's okay, I'll jump in here.
Sure, of course, please, Joe.
Quantum software is definitely something I have strong views on. So actually, at the moment, the current state of quantum software is that, as Michael says, a lot of what people have in mind, perhaps when they think of quantum software, is software packages that are maybe enabling a particular application, that are usually aimed at near-term hardware. They're actually kind of what we can think of as unstructured programs. So they use these variational techniques where they try to learn a quantum program to solve a problem. And that works all right on near-term hardware, although there's no provable advantage for it yet. So we don't actually know that there are the kinds of advantages to be found in this kind of unstructured approach. There are structured algorithms that are known, the most famous of them being Shor's algorithm for factoring numbers, but these are less common. And actually, it's what we focus on at Horizon. We focus on trying to automatically construct structured quantum algorithms for particular tasks. This is less suited to the kinds of hardware we have immediately today. We actually need to push error rates down further in order to be able to run these kind of structured algorithms. And that's where control engineering comes in. That's where improved hardware comes in. So companies like Q-CTRL and the companies focusing on improving hardware, building hardware systems, they're really tackling that end of the spectrum, whereas we're tackling the bridge between kind of taking a classical problem and turning it into a quantum program. There are missing steps in the software stack. So for example, at the moment, one of the key things that is missing that we will for sure need is to be able to take a quantum program and encode it in a way that actively corrects errors. That's still some time off before the hardware is capable of doing that. But that kind of encoding, the automatic decoding and applying these corrections as the system runs, all of that needs to be put in place. There are a lot of research papers on this, but in terms of actual software tools to make this happen, there's still a lot missing. So I wouldn't say that software is running ahead of hardware at the moment. For sure, in our field, theory ran way, way, way ahead of experiment. But when it comes to software, a lot of that theory is in the form of papers, perhaps showing that something was possible, but not necessarily, not necessarily resulting in implementations or things that could run on the hardware if the hardware was there. So previously, my group, when I was still in academia, had taken an example of a paper on machine learning and tried to implement it as a program so that we had the individual instructions. And that took a couple of students like nearly a year to do. Wow. Just because the gap between the level of abstraction in the paper and what you need to turn it into individual gate instructions was very, very high.
Interesting.
So there's a lot to be done on the software layer. But at the same time, the hardware is noisy and imperfect at the moment. And that's something we really need to improve and overcome. But there's a role for software in that. And I think Michael's showing that there's a role for software in that to reduce errors through better control.
Thank you, Joe. Hui Khoon, Mattia, is the mic working right now?
I think it should be working.
Hey, it works. Okay, cool. Hui Khoon, Mattia, you guys have anything to add?
So maybe let me add a bit more to what Joe was just saying about bringing many of these theoretical ideas into actual software that can be used. The same is true for what I work on, which is error correction and fault tolerance. It's really because I also see a question in the Q&A about asking what is preventing quantum technologies from scaling up. This issue of noise that multiple people have talked about already is really the thing that prevents us from doing that. And a lot of the work in the current field is really theoretical. And in terms of bringing the hardware to actual proper usage, being able to exploit the actual quantum advantage that we are all looking for, a lot of that theory also needs to be put into practice. And that's, I think, is the thing that is going to take us a while. Yeah. And then back to your question in terms of realistic timeline for us to expect the quantum hardware to catch up, it sort of depends. It depends on there's hardware and then there's hardware. Like Mike was just saying that there's different kinds of software, right? There's hardware and hardware in the sense that if you're really looking for nearer term things that continues us along this path to more fascinating quantum technologies, but right now, looking at near-term applications, you may be looking at things that you can use already for this sort of quantum simulations, quantum molecular calculations. This can be in the next few years. If you're looking to look at really having a quantum computer that can be a next-gen kind of technology, something that allows you to run Shor's factoring algorithm, the thing that makes us all famous, sort of, right? That's probably going to take a while. Yeah, it probably also requires some sort of a technological, a hardware kind of breakthrough before we can actually get there.
Yep. Thank you, Hui Khoon. Mattia, do you have anything else to add?
I could add a few words.
Sure.
What have been said already is quite interesting and great, but I will just say this, that it's true that on the longer scale, so on the time frame of error-corrected fault-tolerant machine, we have already discovered algorithm, or let's say quantum primitive, that are very powerful compared to classical one. Now we are in this era, which is called noisy intermediate scale quantum computing, shortened into NISQ. And I am of the view that actually on the shorter time frame, let's say the next 5 years, roughly, actually software needs to catch up with hardware in a way. Again, things on the things looks quite different here. We are looking at algorithms that are hybrid, that where CPUs and quantum processing units work very closely. But yeah, I'm there of the idea that in a way, although the quantum resources we have available, the quantum hardware resources look quite different than the one we expect on the time scales, we still struggle to use them. If you think about the proof of quantum supremacy that we have witnessed so far,
yep.
They are all kind of quantum software application where we can appreciate the scientific challenger and the scientific achievement, but people often wonder what's their practical application, right? So I would like to offer this point of for thought.
Thank you, Mattia. And I think you touched on an interesting point, right? In terms of people being very focused on displaying some sort of quantum supremacy, via the different quantum architectures that exist, right? I mean, I think a week or two ago, there was an announcement around, a new breakthrough using photonics, right, as a new paradigm versus, trapped ions and superconducting qubits, but it is all all these are tested in a very specific application, right? There's always one specific thing that they do, and then the rest of the commercial guys will think, oh my god, it doesn't mean anything to us, right? When are we going to be able to do it for something that we understand, right? So is there a point, to these displays of quantum supremacy, and for the average person, in this audience, right? What does it mean to them and the future of quantum computing, right? To see folks who show quantum supremacy, and do the different architectures mean anything at all, to the folks like you guys who are looking at the software layer of it?
It's an interesting question. I think, so the first thing to say is, what is quantum supremacy? Quantum supremacy, very, very broadly, is when a quantum computer can perform a task that is effectively practically impossible for even a really big supercomputer. Right? There are a few different definitions, but that's broadly it. And so Google did a demonstration a year ago or thereabouts of performing a calculation that was effectively impossible for any practical supercomputer. And a team in China has done something very similar recently. Now, the important thing to say is that, as was prefaced in the question, this does not mean it's a problem that anybody cares about. It's a problem so far that is largely designed to answer a science question, where the science question is, can quantum computers in principle do really big things? Now, it also speaks to an engineering accomplishment. It says that we can build systems that allow the manipulation of particles and systems that obey the rules of quantum physics at such a scale that we can, in principle, achieve this kind of computation. That is really an astonishing scientific demonstration. Now, how does one extrapolate from that to practical applications of quantum computing? That's where we begin to draw a long bow, where it's very difficult to make that link, because in many cases, the hardware one builds for a quantum supremacy demonstration may not look anything like the hardware one builds to solve a problem of interest. That's certainly true of the photonic implementation as demonstrated so far, but it's in general, I think, a true statement. overall, it's, in my view, extremely important to come back to that key point. Quantum supremacy is about science. It is about a scientific marker in our progress in the field. It is not about commercial relevance. And yet, of course, we are all thinking that there will be lessons learned from achieving that then flow on to the development of the next and the next generation of quantum computers that try to chase a different target, which is sometimes called quantum advantage, which is where it is economically or practically relevant to choose the quantum computing version instead of the classical, conventional machine learning or whatever algorithm, because you get the solution faster or cheaper, or it's something you just couldn't do. Even if, remember in my talk, I showed the pixelated image, even if you're only getting another approximation, if your approximation is better, that can be an economically relevant win, even if, it's not an impossible calculation in the context of quantum supremacy.
Thanks, Mike. Anyone else? Oh, Joe, I think you're on mute, Joe. This must be the number one word, phrase on Zoom.
Can you hear me
I think
now?
you're on mute. Yes, perfect, Joe.
Okay, sorry about that.
No, you're good.
My mic timed off. Okay, so if it's okay, I'd jump in here because I agree with what Michael said, actually, but there's some more I would add. So, as Michael said, quantum supremacy was essentially a milestone that was hit that showed that for the first time there was quantum hardware that was capable of doing things that could not be done on a classical computer. And there is this further milestone that we're looking to in the next couple of years that we call quantum advantage, which is where it is shown for the first time to be to actually represent an advantage in terms of calculation according to some metric, whether it be cost, whether it be time, on some kind of relevant problem. The demonstrations of supremacy so far, both the boson sampling one that just came out and the Google one previously, but
Oh, sorry, Joe. You went off again.
We lost him again. What's going on today?
This is the day, man. I think Murphy must be in orbit today.
okay.
Okay, here we go.
Sorry, the battery died. Okay, so the two milestones we have supremacy, where for the first time we've shown that hardware exists that is capable of doing interesting things, things that you can't simulate, but not necessarily things that are useful. And the next milestone we have is showing that we can use hardware that we can build to some advantage for some relevant problem. And I agree, until we've met that second milestone, it's not really something that's going to have a commercial impact. But what I would say is that this first milestone, the supremacy milestone, is actually a very, very important one for the field, both from a scientific perspective, but also for startups and for others in the space. Because what it really does is it starts to put the ball into the court, not of the hardware companies, but into the court of software companies. And into the court, not just of startups and software companies, but into the court of theorists again. It's the point to show, we know there are these systems that are hard to simulate. Can we do something useful with them? We don't know how to at the moment, but can we take advantage of them? Are there new applications that are unlocked by them? And that's something that's a software problem. That's something that's a theory, an algorithms problem. And it's something that can be solved on pen and paper. It's something that can be solved in code. It's not something that necessarily needs hardware advances in order to happen. And I think for that reason, it's a very important milestone.
Thanks, Joe. Hui-Khoon, Mattia?
Yeah, I would like to add a point to what Joe just said. There are at Cambridge Quantum Computing, we're very focused on a number of applications, machine learning, combinatorial optimization, quantum chemistry. And I would like to focus particularly for the near term, and in the case of useful application, on chemistry and on combinatorial optimization. So on chemistry, there is a wide consensus that once we have maybe a few hundred qubits, we should be able to do quite accurate calculation for systems that are out of the reach of classical algorithm and classical APC. because basically we can quantify the role of the quantumness of a system in the calculation quite accurately. We know, apart from superposition, but also how important is entanglement to describe a system, and we know that describing entanglement using a quantum computing is quite natural. The other aspect is instead in combinatorial optimization, it's an interesting field, is a field where we don't expect quantum computing a priori to be better than classical one. And most of the algorithms to solve those problems are heuristic algorithms. There are some early indication that quantum algorithm could scale, let's say in runtime, better when we reach the hundreds of qubit size of the system there too. But that will be an experimental proof. We'll be able to show it once we have a few hundred qubit that work. Perhaps they're, I strongly hope that we should be able to do something without error correction. So this will be an experimental proof that comes on the software side, let's say. Thank you,
Mattia. Hui Khoon?
And I just have a point to add, which is to sort of, I agree with Joe actually that these quantum supremacy points, these milestones are extremely important ones. Mike, of course, points out that they are scientific milestones, which is yes, but I also think that even to the commercial and industrial world, there are clear expressions of progress. This is what I see it as. Because I mean, the quantum technology has been developing sort of in the background in university labs for a very long time, but without having a clear goal in mind, without having a clear statement of a problem, what is it that quantum computers can do? I think it's very difficult to communicate the actual state of the art of the engineering and the science. So these sort of quantum supremacy things, and eventually the quantum advantage that Joe had talked about, these, I think, is a way for the scientists, for the researchers to signal where we are at. But at the end of the day, when you want to ask yourself, if I were a company, I'm trying to think about what I can use quantum computers for. The thing that you need to ask yourself is whether or not quantum computers adds a tool to your toolbox. I'd like to not think so much in terms of quantum advantage, quantum supremacy, what is it that quantum things can do better than classical things can do. I like to think about what is it that quantum might be able to do more easily, more naturally. Okay, and sometimes it may not actually be that much faster. Speaking from like a theoretical computer scientist perspective, it may not be faster to that person, but it may be easier for you to implement. It may fit more naturally with the problem that you have at hand. This was what Mike had said early on in terms of these quantum calculations for pharmaceutical companies. It's a much more natural thing to think it in terms of quantum calculations than to try to fit it onto the classical computer, right? So in that sense, I think the question that you need to ask yourself is quantum computers useful to you? That's the kind of question I want you to ask, whether or not it's easy or more natural, not whether or not it's more supreme or more advantageous. Yeah.
Thank you, and I like that. So I think that's a great segue for us to move away from the slightly more abstract discussion into kind of like a more commercial discussion, right? So the one thing that will keep the quantum industry alive is if commercials and the industrials are able to understand how quantum fits into their longer roadmap. Right, and in this sense, this is something that investors also struggle with, right? Is in that the technology is a distance away, So how can we, how would companies, startups, entrepreneurs build up a roadmap, a developmental roadmap, or a pipeline, right? In working with these commercials, and how should commercials start to think about engaging with a lot of the quantum related startups in the scene, right? What does the process look like to you, and how do you think it needs to keep evolving to get to a point of maturity? We all know that it's not going to make money any point soon, right? But I think we need to figure out how can we encourage more people to come in and experiment, right? And then what does the experimentation look like, right? Other than them having a whole team just thinking about, how's quantum going to be a more a natural fit for their arsenal of tools, how would you guys think about it, and how would you encourage, MNCs, commercials to kind of think about, how to deploy? Anyone can take that. And just time check, we have about 10 minutes. I'm gonna stick on this question for a while, and then I'll try to save a little bit of time for the Q&A.
Maybe I'll chime in. I mean, as an industrialist now, like others on the panel, we obviously all want to say, quantum is for everybody. It's great, but the reality is it's not, right? And it's not any more than like if you run a cafe, do you need AI? Probably not, right? There are some tools that indirectly may leverage it for the web optimization or whatever, but overall, quantum computing is a tool for organizations that have heavy computational burdens. Mm-hmm. And those are clearly industries in finance and banking, in industrial chemistry, in pharmaceutical drug design, where computational bottlenecks are endemic to all of the challenges that these companies are trying to overcome. Mm-hmm. Quantum companies like ours, those on the panel, we often are building solutions that are relevant to this. I think that the trick is, one needs to determine if they should make an investment early. In many cases, it makes a lot of sense if you're investing in other computational tools that are really on the edge of capability, that quantum computing can be one related tool in the toolbox, like we heard just a moment ago. But an important thing to keep in mind is sometimes engaging with startups is exactly the right thing to do. But startups that are asked to do a lot of consulting don't live very long, because consulting is not scalable, right? I can charge X times my hourly rate, and that's about it. So the real question is, how can you find tools that, coupled with a little bit of consulting, can help you solve your problems? So for Q-Control, we have a tool called FireOpal, which is allowing all of our fancy control theory techniques to be leveraged by end users who don't even understand what a qubit is, right? That's the idea, abstracting away. And you'll see similar things for different problems in quantum computing, like Joel's tool set or things at CQC. But really the idea is start looking at the tool set and then how some assistance can help in terms of identifying the right problems that can be solved for your organization.
Thanks, Mike. Anyone else?
Yeah, so I would agree with what Michael said, particularly in terms of the relationship between consulting and automating tools. And indeed, where our tools come from is trying to automate what you would do as a consultant if you were asked to construct a quantum algorithm. So if someone comes to you with a particular problem and they say, we'd like a quantum, can quantum computing tackle this? How do we approach it? Well, if you were a consultant, what you might do, the first thing you might do is you might ask them for their code and say, how do you currently solve this problem? And then you'd look for opportunities for quantum speed up within that current solution. And that's exactly what we're doing with our tools, to try to make it much more accessible to a larger group. But it's certainly the case that the industries where this will be most relevant are the industries that currently make large use of high performance computing, particularly for problems that have small inputs and small outputs, not for high throughput stuff. The other thing I would say is that there's also another category of things, which is those industries where there are problems that would be computationally intense, but they are so computationally intense that they're impossible to solve at the moment. And so I think quantum computing is also going to open up some of these in terms of larger scale modeling as the technology matures, but not at the early stage. One point where I would differ from Michael's thinking is in terms of the applicability of quantum computing. So in his talk, he brought up the use for particular areas like simulating quantum chemistry. And chemistry and optimization are areas where there has been a lot of research into the use of quantum computing. So I fully agree that those are areas that will be impacted. However, one of the things we've been doing at Horizon is to construct quantum algorithms from general code. And that means taking things like for loops and recognizing how to break them apart and how to accelerate them, how to use amplitude amplification techniques, for example, to turn them into quantum algorithms that run in less cycles. And, as we look towards the longer term with more structured algorithms, I think actually the opportunity for quantum speedups are very, very widely applicable. And I think that's something that's underappreciated today. And so I think really for us, cracking that nut will be a key to our success, but it will enable much more adoption within industry as the technology matures.
Thanks, Joe. Mattia, Hui Khoon?
Sure. I often talk with multi-billion-dollar per year revenue businesses. They have large R&D budgets, and one of the questions that comes up within this interaction is that these businesses have really hundreds or if not thousands of software engineers, and they say, okay, can you help us train a team of quantum software engineers, right? And so that then we will kind of, these are bright people, intelligent people that will come up with some algorithm, some solution themselves. That approach is not the most convenient, if you ask me, because building quantum algorithm for NIST devices, it's even more complicated than writing in assembly code. If you look on the other hand, though, at perfect, let's say, error-corrected, fault-tolerant computer, we know that the best algorithm that we have so far came from very, let's say, deep theoretical insight into quantum information, which again doesn't sound to me, at least, the kind of job that a software engineer or a quantum software engineer will do. What I often advise in this collaboration is that the industry partner should act as the domain experts. So people that know their problem inside out, they know how to engineer it in order to really select which part of the problem need to be retained in order to be meaningful, and which other part of the problem can be eliminated in order to make the specific problem more suitable for the quantum computer we are available type right now. And the key piece of advice that I offer is that everything else is done by quantum software companies, such as, of course, Cambridge Quantum Computing, where we will create a new quantum algorithm from them. And by new quantum algorithm, I really stand by what I said at the beginning, that the quantum software need to catch up, right? By new quantum algorithm, I mean by going back to the drawing board and basically creating something that is publication worthy and can really go into the direction of showing quantum advantage in a very focused, specific industrial instance. But that requires really, that kind of expertise that I believe right now is found only in academia or in those academics that then join startups such as at Cambridge Quantum. We more than half of our workforce has PhDs. So, and also in various disciplines, from computer science, complexity theory, quantum information, condensed matter, machine learning, this kind of stuff.
And we could maybe just to close up this particular discussion on what gentlemen have shared, from your perspective as an academic, someone as a researcher, how should corporates and enterprises look to work with you guys, right, on a much longer term solutions or projects?
So I think of course a lot of it is about communicating what is it is of interest, in fact, to the companies that may be looking at quantum technologies. And actually, I would say that it's more the other side where the academics need to listen more. Yeah. So in fact, because here in Singapore, we have been doing this quantum engineering program thing is just starting up. I know that Joe is also sort of involved in it. That actually has been an excellent opportunity for the academics like myself to really listen to the industrial partners to see what they need. And in the other direction is also an excellent place for us as academics to sort of convey what is possible and what is not possible, to sift out really what is the truth from all the hyped up things that we hear so much about in the media, right? So the only thing that I can really say is communication. I really don't think that we do that enough. But of course, the field is getting a lot better at doing this right now than we were, say, 5 or 10 years ago. Yeah.
Thank you. So we are actually at the end of our time. If you guys don't mind, if I take like 5 minutes, to just maybe answer 1 or 2 questions from the Q&A. We have a whole bunch of questions. I'm going to take the highest rated ones, just to be fair to everyone. So the first one is, what's an overview of problems which prevent quantum technologies from scaling? I think some of you have answered bits and pieces of that, but if you could answer in a very short way, what in your perspective is the key problem that prevent quantum technology from scaling?
It's really hard. It's really hard to build. My academic team is experimental. We build trapped ion quantum computers. It is really, really hard to manipulate individual particles of light and matter because everything around them messes them up. All the fluctuations in the environment mess up the performance of your hardware. This is why we started a whole company focused on making quantum hardware perform better, whether it's in computing or sensing. But fundamentally, we're building really complicated machines.
And just to add on to that, right? Is it a problem where no matter how many brains I throw at it, it's not going to get solved faster, right? It's just so complex that the brains don't really, the quantity of brains don't really matter.
I think in some respect, the answer is yes, that just throwing people and money at the problem doesn't fix it, because that ignores the importance of serendipity and creativity in the process. This is not pure engineering where you just, I have 1,000 different things to test and I need to go 1, 2, 3, 4, 5, 6. In many respects, it's new discovery, and it is very likely, in my view, I don't know how others feel, that the quantum computers that eventually get us to really solving useful problems are not likely to look particularly like the machines we're building today. They may have some elements, they may have some components, but I think there's a very significant discovery process involved.
Thank you. Anyone else has an answer for that? A different one?
So, as Michael says, controlling quantum systems is hard. There's a number of specific problems for each technology. There's a limit to how much you can put in a dilution refrigerator. If you're talking about microwaves, there's crosstalk problems. If you're talking about ions, there's problems cooling them, and you have to move to segmented traps or some other kind of system. Michael is far more expert than me in this, so I'll defer to him on that. But there's many different problems for different systems, and it's, we're slowly overcoming them, but it's a slow process. Now, whether capital and additional manpower can change that, I think capital can. So one of the things that happens, particularly in academia, is that people build a setup and then they keep that setup for a long time before they have to dismantle it and build a new one and try to get as many papers out of that as they can. And I think if there was unlimited capital and unlimited space and unlimited talent, then that would not necessarily be the case, and you would see more parallel development. I think you would see more systems running in parallel, and you start to see that with some of the large companies in the hardware space, where you will see many Dill fridges set up, for example. And I think that is something where capital does have an impact, but there's not many people that are talented in these areas, that are not talented, but that are experienced in these areas, that have the necessary background to tackle these problems. There's only a few teams, and the same. I'd like to think the same on the software side, but the reality is that there's relatively few teams, and you could better resource those teams, but you can't start. There's not so many more people that you can find another 100 groups to start up from nowhere that can all be world leaders. That's just not the case. It'll take 10 years to get them up to speed.
Thanks, Joe. I'm going to just throw one more question in, right? What are the advantages and disadvantages of? Okay, so basically this question is, if I were someone wanting to enter the industry, right? What is the advantage or disadvantage of being in a quantum startup versus joining a big player like a Google, IBM, and being part of their quantum project? Yeah. So you guys are founders. We have we have Cambridge Computing, and we have a researcher. What are your perspectives on this?
So if no one's going to jump in, I will. There's two. Well, aside from ESOP participation, there is another major advantage to a number of quantum startups, and I think you see that reflected in two of the the startups on this panel, about Horizon and Q-CTRL, which is that they're led by scientists. And I think in the early days of this technology, I think that's important. It means that when there are scientific barriers, when there is potential to do things in a new way, where there's potential for innovation and so on, you will find an ear that listens, that's receptive. You also have people that are aware of the capabilities and the challenges facing the technology that are in decision-making positions. And I think that's critically important at this stage.
Thanks, Joe.
I think those are really interesting insights. Oh, I'm sorry if I.
No, go for it.
Maybe I'll add to it and try to be a little more fair to the other players in the ecosystem. So first of all, in a startup, it's really hard to hide, right?
Yep.
If you want to disappear into the woodwork in a really large organization that's going to let you do quasi-academic work and on your own and publish some papers, that's pretty difficult in a startup. Now, the converse of that, of course, is that your impact is visible, right? You're not one of 1,000 in some giant machine. You can say, "Oh, I built that module in the product that was released today," right? That's extremely empowering. It's extremely exciting. I also worked very hard to make Q-CTRL exactly the opposite of everything I didn't like about university life. So no bureaucracy, none of the horrendous, policy-heavy approaches to existence that made my life so miserable. It's very common in the university. It takes months and months to make a postdoc hire. I hired 5 people in a day, and they started the next week at Q-CTRL when we were very early. So, that ability to move fast, it's very different. And the reality is, when you're working in a big corporate, whether it's a more incumbent industry like IBM or a newer at this point company like Google or Microsoft, someone else, those are big, like really, really big organizations, and they can be very bureaucratic. And so if you want an experience where those things are streamlined and you don't have to deal with them, startups are awesome. Of course, the flip side is you don't get the same perks, right? So, it's very much the choice of the individual, what they resonate with.
Cool. Mattia, Hui Khoon, any last words?
Absolutely. I would say that, as Joe said, let's say with a different choice of word, I would say that it's very important to be science-led and a science-first organization. Maybe it's not as important if your CEO is a scientist or not, but it's important what's the weight of the science, how it's important for the startup to demonstrate to be leader in their own field. That's certainly a key aspect. I really loved what Michael said about, this kind of a make or break attitude of, in a way a startup has to prove themselves. They need to show to all the stakeholders that what they do is really valuable to all their clients and investors sort of every day. And they have to provide a direct and tangible, valuable, while perhaps in bigger corporation, it's more about commoditizing something. And even when it comes to perks, I would say, I think that the amount of investment and money that is flowing in the quantum industry, in the quantum startups, probably it is making this industry attractive and competitive. Also, with bigger businesses. At least that's my insight. Also, maybe from third parties. I think that a startup will be very, in a way, again, dedicated to solving their client problem, much more maybe to big corporate, which have a sort of marketing agenda or some sort of PR agenda there, where they want to, establish, prove also something else, or establishing a sort of image of themselves to the wider public. Many different thoughts, but we're running out of time.
Thank you, Mattia. Hui Khoon, I'll let you have the final word.
No, I'm afraid nothing for me. I'm happy to hear my fellow panelists tell me what I should say to my students the next time I get this question.
Nice. And so guys, I lied when I said it was going to be 5 minutes. It was 10, but I did not lie when I said that this was going to be an awesome discussion, right? So I hate to stop this right now, but unfortunately we have to. Thanks so much everyone for being with us today. You know, Mattia for getting up in the middle of the night to do this for us. You know, and thanks to all the audience for being here today. Do remember that the Deep Tech Summit starts tomorrow. The sign up link is in the chat, so you